All right, today we're going to talk about solubility rules, and I'm going to give you some tricks to memorize them because you will have to know your solubility rules, and that's going to be important for the success in what we're doing today with Jeanette Ionics. And then we're going to run on and do some stuff over, I can't even think today, Stoichiometry using information we know about solutions. So solubility rules. There's some rules that are, one rule specifically, the Big Daddy rule, which is super important. Here's Big Daddy. He's a solubility pimp right there. He's got his cane and his hat. And Big Daddy rule basically says that alkali metal salts, meaning group 1 metal salts, and ammonium-containing salts, as well, and I kind of combine these, the nitrate ion, and this is the acetate, even though you don't recognize it. Acetate. And this is when these are in salts, not in acids or bases. So alkali metals, ammonium, nitrates, acetates are all going to be soluble all the time. All right? And that is the Big Daddy rule. You can cross out number 3. We don't worry about that. Chloride, bromide, and iodide are soluble except for silver, mercury, and lead. What are chlorine, fluorine, and bromine? What are those? Halogens. So there is a little saying, it's crazy, and if you want to come up with something else, you can to remember this. But Hal hates, or hugs, I'll say hugs, Aggies pretty badly. What the heck is that? Well, halogens, all halogens are soluble except for mercury, silver, and whenever you see pretty badly, it's lead. PB. All right? So Hal hugs Aggies pretty badly. We do have a picture of Hal. Hal is right there. Hal's kind of a hippie, and he's got an A&M helmet. He's hugging the A&M helmet. So Hal hugs Aggies pretty badly. He doesn't know how to hug them. So these are the things that are not soluble. So the next one is going to be things that are not soluble. So all halogens are soluble except for, and we're talking about in salts, mercury, silver, and lead. The other one you need to know are the sulfates. Most sulfates, there it goes. Most sulfates are soluble except for calcium, strontium, barium, silver, mercury, and lead. You think this one was bad? Wait until you get to this one. So let me write this is we know mercury, this is we know silver, this is no. All right, so all sulfates are soluble except for, so Sol is a man's name. Sol can bag hags pretty badly. It gets worse in Sri Lanka and Argentina. There's Sol. He's putting a hag in a bag. She's like a witch in a bag. So what this stands for is all sulfates are soluble except for, what is this one? Calcium, barium, mercury, lead, strontium, and silver. Okay? You're more than welcome to come up with your own sayings. And if you come up with an amazing one, let me know. I'm all about adopting new ideas. Okay, so utilizing, those are the main ones. And most of the other polyatomics are going to be insoluble. But remember, Big Daddy, Rule 1 takes priority. So if any of these are attached to a group 1 metal, it's going to be soluble. And Big Daddy is the one that is going to be the most useful rule for you along with the two sayings. Those are the ones that you're going to use most often. So this is solubility in water. Determine which of the following compounds are soluble in water. Silver nitrate. Guess what? Soluble. So you need to be careful when you're taking tests, because the fact that someone just said yes reminded me of last year on the test when the question is the following soluble or insoluble? And students answered yes. That's not an answer to that question. So let's answer the question. In this case, silver nitrate is soluble. Why? The nitrate is always soluble. It's part of the Big Daddy rule. Sodium chloride. Soluble. Why? Sodium. Lead 2 bromide. Soluble or insoluble? Insoluble. Why? Bromide is a halogen, right? Hal hugs Aggies pretty badly. That's the pretty badly. PB. Ammonium, so this we said was soluble, soluble, insoluble. Ammonium hydroxide. Soluble. Why? Ammonium is part of the Big Daddy rule. And then barium sulfate. Insoluble. Why? Because of barium, but because barium is attached to sulfate. Sul can bag hags. All sulfates are soluble except for calcium. Barium. There it is. Insoluble. And then calcium hydroxide will go either way, but the truth of it is, if calcium hydroxide is in a dilute solution, we say it's 100% soluble because it has some space to dissolve. Where calcium hydroxide falls under is weak or strong acid-base categorization. So strong bases are considered soluble, right? Okay. This was one of those I said could go either way. So it is, when the solution is dilute, like 1 molar or 0.5 molar, we say it's soluble. But if you have like a 10 molar solution, most of it won't dissolve. That makes it insoluble. So just know this can go either way. But as far as the bases go, any group 1 hydroxide is 100% soluble because it's a strong base. And then lithium carbonate. Soluble. Why? Group 1, Big Daddy rule. Okay? All right, so are we good with that? All right, now we're going to jump in and start doing some net ionic equations. Can't see. And with these, I'm pretty much just going to do the first one for you, just to kind of remind you what you need to do. The first thing we're going to do is we're going to write the molecular equation, meaning we're going to write everything along with the state of matter that it exists in an aqueous solution, and then predict the products. Most of these are double replacement reactions. You shouldn't have trouble predicting the products. So we're going to start, and we're going to write potassium chloride, KCl. When I put that in water, what is that? It's aqueous. It's soluble in water, so we're going to write AQ. If it's soluble in water, we write AQ next to it. If it doesn't dissolve, we write solid next to it. And then if it's water, like pure water we're making, it's liquid, or if we make CO2, that's a gas. So they're all going to kind of make sense. So we're combining it with lead 2 nitrate. Does lead 2 nitrate dissolve? Aqueous, yes. So what is that going to make? Double replacement. Come on. We'll balance it in a minute. Just tell me the compound. KNO3, and that's always soluble, so that's aqueous. And what's the other thing it makes? PbCl2. Good. What's the state of that? Does that dissolve? No, it doesn't, because it is a halogen. Hal hugs Aggies pretty badly. That does not dissolve, so we write S next to it. So before we continue on, we are going to go ahead and balance the equation. We have 2 nitrates. We need 2 nitrates. That gives us 2 potassiums. We need 2 potassiums, and my chlorine's balanced when I did that. So now the next step is the complete ionic equation. All we do here is we split these up into ions. You have to keep the state of matter written next to them. So I'm going to split this up. When I split up 2 KCl's, do we get that I get 2 K pluses and 2 Cl minuses? So this 2 has to be carried to both of those ions. So we get 2 K plus aqueous. Whatever this is, we're going to write it again, plus 2Cl aqueous. This is aqueous, so I'm going to split it up. So I get Pb plus 2 aqueous. What also translates is this means we have 2 nitrates, so that has to be carried as well. 2 nitrate aqueuses. Do y'all see that? I will not accept it if it's a subscript. Any mistake like that. This is now, you guys are beyond making mistakes like forgetting charges, like not doing subscripts. Okay? All right. 2K plus aqueous plus 2NO3 minus aqueous. What do I do with this PbCl2? Leave it alone because it is solid. It does not. It's going to form, what's that thing we call? Yep, it's going to form a precipitate. So this is the total ionic equation. What do I do to write the net ionic equation? Exactly. Cancel out the ones that are the same on both sides. What was that funny name for those? Yep, spectator ions. Let's get rid of our spectators. To cancel out spectators, they have to match identically on both sides. It's got to be the same state and the same number and the same charge. So nitrates go and potassiums go. So my final net ionic equation is 2Cl minus aqueous plus Pb plus 2 aqueous gives us PbCl2 solid. Okay? Is it easier than last year? Now that you've done it? All right, let's do the next one. We're going to do 4 of these. Silver nitrate and magnesium bromide are mixed. Silver nitrate, based on solubility rules, what do I write as its state? What I write aqueous. Yeah, I have some students who say soluble and write S. Be careful. That means solid. So if it dissolves, it's soluble, it's aqueous. Magnesium bromide is MgBr2. And what is its state? It's a halogen. But is it one of the 3? All halogens are soluble except for hugs Aggies pretty badly. Is it one of those? Nope, so it is aqueous. Now, what are my 2 products? Double replacement, guys, come on. Silver bromide. Is that, what state of matter is that? It is not soluble halogens. It's the Aggie. Hal hugs Aggies. And then, what is my other product? AmGNO3, 2, and this is aqueous because all nitrates are soluble. So we have to balance this. We need 2 nitrates, 2 nitrates, 2 silvers, 2 silvers, and my bromines are balanced. Okay, so now I'm going to do my total ionic equation and start busting stuff up. This is aqueous, so I'm going to get 2Ag plus aqueous plus 2NO3 minus aqueous plus Mg plus 2 aqueous plus, big student mistake here is writing Br2. It's not. It's 2Br minus aqueous. Gives you, what do I do with this guy? Leave them alone. 2AgBr solid plus 2, I didn't mean to do that, plus Mg plus 2 aqueous plus 2 nitrate aqueuses. All right, what are my spectators? The nitrate, we said nitrates are always soluble, right? So won't nitrates always be spectators? And what else is a spectator? The magnesium ions. Leaving me behind my final net ionic of 2Ag plus aqueous plus 2Br minus. I'm not going to mark you wrong, but it would be better to reduce this to Ag plus Br minus makes AgBr. But again, it's not wrong. This is still a balanced equation. And I know why it's like that. Okay, questions? Okay. Now let's move on to ones that sodium chloride and lithium sulfate are mixed. Let's take a look at this. See if we can see anything special about this one. Sodium chloride, what do I write? Right after that. Aqueous. Lithium sulfate, Li2SO4. What's its state? Aqueous. Double replacement, what's one of our products? Na2SO4, what's its state? Aqueous. And then the other one is what? Yep, LiCl, and what is its state? Aqueous. You see these are all group 1 metals? All right, so I could go and do this, but is this balanced, by the way? No, we need to balance it. We need a 2 there and a 2 there. So I could go and split this up, but what's going to happen when I split it all up? It all cancels. So what we say, this is no reaction. Nothing happens. All these guys just split up. All ions split up and float around in solution. So what this would be a good problem, I could see them potentially asking you to draw what's in the beaker. So I'd need to see all those ions in the beaker with no solid precipitate being formed at all. Okay? Let's keep going. Doop. Acid-base neutralization reactions. Do I go on? Hold on. Let me see. I feel like stoichiometry is a separate day. No, I keep going. I go through stoichiometry to the conductivity thing. Wow, it's a lot. Okay, so here we go. This is acid-base neutralization. I don't want it to scare you. It's still a double replacement reaction. When you mix an acid and a base, what do you always get? Water and a salt. So we're always going to get salt and water as our products. The salt isn't always going to be sodium chloride. There's different salts out there that we might produce. So one thing we need to pay attention to is if the acid is strong, or base is strong, we're going to write aqueous next to it, and we're going to break it up in the next step. Okay, that makes sense, correct? Now, if the acid is weak, we're going to write AQ next to it, but it dissolves. But remember, because it's weak, what does it mean? It doesn't completely dissociate, so we're going to leave it together in the second step, but still have AQ next to it. These things are still dissolved in solution, but not in ions. So that's going to be something you have to pay attention to anytime you do a net ionic with acids and bases. All right? So sodium hydroxide, what kind of base is that? Strong base. So we know that's going to dissociate 100%. So what do I write next to it? AQ. Mixed with phosphoric acid, H3PO4. So this is a strong base. What is phosphoric acid? A weak acid. We are still going to write AQ next to it, but because it's weak, when we get to our next step, you're not going to break it up. You're going to leave it as it is. And then we do our double replacement, and what do we get? Na3PO4, that's our salt. It's a group 1 salt, so it's aqueous. Plus, what's our other one? Water. Right. You can write it like HOH if it helps you see it. And I kind of suggest in these writing water as HOH because it's going to make the balancing easier. What is the state of matter? Liquid. Correct. Water is a pure liquid. Okay. So Let's break up things we can. Oh, is this balanced? We need 3 NAs. We need, you see how the OH here balances with this OH? We put a 3 there. It just makes it easier to balance. Okay, so 3 Na plus aqueous plus 3 O minus aqueous. This is where you have to be careful. It is a weak acid, so we leave it together, but we still write aqueous next to it. So what do we do with sodium phosphate? It's not rhetorical. What do we do with sodium phosphate? Break it up. 3 Na plus aqueous plus PO4 minus 3 aqueous plus 3 water liquids. And we leave that together, obviously. So what are my spectators this time? It's only sodium ions. So those go. So my final net ionic is 3 hydroxide ions, aqueous, plus H3PO4 aqueous gives us, I skipped the phosphate, 3 waters plus a phosphate, aqueous. All right? I want to change this one here. I want to make this hydrochloric acid real quick to prove a point. So change your acetic acid to hydrochloric. All right, let's classify my acids and bases there. What kind of acid and base do I have? Strong acid, strong base, right? So HCl is going to be considered aqueous, and KOH is going to be considered aqueous. Why did I put a thing there? It's going to be considered aqueous, and both of them are strong. So this is a strong, strong mixture. You're going to hear that a lot when we get to acid-base. Strong, strong, weak, strong, all that jazz. So this can occur by a single replacement reaction, a double replacement reaction, and what do we make? What salt? And I can write this as HOH for balancing purposes if we want. All right. So because these are both strong acids and bases, I can split them up. This is a balanced equation already, I think. Yes, it is balanced because everything has a plus or minus 1 charge, so we're balanced. We have H plus aqueous. Because it is a strong acid, it will 100% dissociate, plus Cl minus aqueous, plus K plus aqueous, plus OH minus aqueous gives you H2O liquid plus K plus aqueous plus Cl minus aqueous. What goes away? Yep, your potassiums and your chlorides, leaving us the following equation. What did we just do then at the end of the day? We made water. That's why this is called neutralization, because we're making water. This right here is the net ionic equation for all strong, strong acid-base reactions. No matter what strong acid or base we use, we always end up with this equation. Okay? For all strong, strong reactions. Does that kind of make sense why that would happen? Right? Yeah. You know what? If you recognize it, I make a statement like strong acid, strong base, so I know that you at least thought about that. Because if you do that by accident on the one above, it could be minus 20 points. So you got to be careful. Okay? But yeah, if you recognize strong, strong, and know that that's going to be the net ionic, you can jump to that point. Just make a note that you recognize that, okay? All right. Let's move on. So everyone, now this is just going to take you practicing. I think you got a really good coverage of that in Chem 1, so we don't need to beat a dead horse on this. All right, we're going to do a couple of these problems. How many? We're going to do 3. No big whoop. Calculate the mass of silver sulfide produced when 18 grams of silver nitrate is added to excess silver sodium sulfide. So what's our first step in this, do you think? Writing a balanced equation. So we are producing Ag2S. And what is Ag2S if we're making, it's probably going to be a solid, which it is, but we really don't need to worry about states of matter here. I can get that out of my brain. When 18 grams of silver nitrate, so we're looking for mass of this, when 18.0 grams of silver nitrate is added to excess sodium sulfide. What is my other product? Yep. Okay. So, in order, we needed the rest of the reaction so we could balance this. And we need a 2 here, and we need a 2 here. So, this is easy because we don't have to find a limiting reactant. We can just do stoichiometry straight to there, right? Okay, so the only difference between this and what we've been doing is we're not giving you the whole reaction. You have to write the reaction yourself. So let's do this. Start out with 18.0 grams. You guys need to check my math when I had the numbers, and I'll just throw them up here, but be checking my math behind me and make sure I don't do it wrong for the video that's going on right now. AgNO3. Okay, what do I convert to first? Grams per mole, right? So for every 1 mole of AgNO3, I have 169.88 grams of AgNO3. Now I mole bridge over, right? And for every 1 mole of what I'm looking for, Ag2S, there are 2 moles of AgNO3. Do we see that based on the stoichiometry? Yes. And then we convert those moles to grams. So there are 247.81 grams for every 1 mole of AgS. Go ahead and check my math here and make sure I get the right answer. How many sig figs in our final answer? 3. I got 13.1 grams of silver sulfide. Okay, good. All right, questions on that one? Pretty simple. All right, 2 more problems. Yay. Oh, let me pull this puppy up. All right. What mass of iron 3 hydroxide is produced when 35 mils of 0.250 molar iron 3 nitrate is mixed with 55 mils of 0.150 molar KOH? All right, so we're mixing iron 3 nitrate, so FeNO3 with KOH to make FeOH3. And what is my other product? KNO3. So to balance this, we need a 3 there, and we need a 3 here. So let me jot down the information. I have 35 mils of this at 0.250 molar mixed with 55 mils of that with 0.180 molar. What is the mass of this produced? What do you think the first step of this problem is? Yeah, we got to find the limiting reagent because we have 2 different molarities and 2 different amounts. So just think back to finding limiting reagent. What did we always have to find first? Moles. So now we're finding moles, but we're using just different things to find moles. So remember, if I have 0.035 liters, you okay with that? what I just did there, times the molarity of 0.250 moles per liter. That multiplication gives me moles. So what is the number of moles of iron 3 nitrate? 0.00875. That's what I got. And then I do the same thing here. I have 0.055 mils times its molarity of 0.180 moles over liters. I got 0.0099. 0.0099 moles. Once we know moles, can I just say which one runs out? What else do I have to consider? Exactly. For every one of those, I use 3 of those. So I divide this by 1, divide this one by 3. This comes out to be like 0.00875. What is this one? 0.0033, right? So this one is smaller, making this the limiting reactant, and this one then is in excess. So now I do stoichiometry from here, boop, all the way to there. Whoa, that really jumped up. Okay, so let's start with the moles. You okay with that? 0.0099 moles. And this is moles of KOH. For every 3 moles of KOH, I have 1 mole of FeOH3. And then for every 1 mole of FeOH3, I got a molar mass of 106.88 grams for a final answer of 0.353 grams of ferric hydroxide. That would be iron 3 hydroxide. It's a lot, I know. Sorry, I'm like fanning myself and it's making a loud noise on the video. It's going to be very annoying for people. Okay, this next problem, don't let it scare you. It's actually not that bad. You're going to be able to see number 10 right above it, so you're going to be looking back at number 10 for me while I pull up number 11 here. From the previous problem, calculate the molarity of the nitrate ions in the solution after the reaction is complete. Here's the thing. Nitrate is always what? It's always soluble, right? So whatever nitrate we put in at the beginning, isn't it the nitrate that's still floating around at the end? So all we really need to do is find the nitrate ion concentration after we mix the two, because we have what's our concentration of nitrate? How do I figure that out just in the FeNO3 Look it up. It's 0.250 molar FeNO3. So what would be the nitrate ion concentration? For every one of those, I have 3 nitrates, so it would be 3 times that, right? I can't just do that, though, because what did I do when I mixed the two? What did I do to the nitrate when I mixed the two? I increased the volume, which did what to the concentration? I diluted it, right? So we basically have to do a dilution calculation to figure out what the concentration is after the dilution, all right? So here's what we're going to do. We know our original concentration is 0.250 molar FeNO3. Is everybody with me there? Okay, so let's find the concentration of FeNO3 after we dilute, after we mix the two. And to do that, I am going to use what equation? Yep, M1V1 equals M2V2. So originally, I have a 0.250 molar. How many mils of the iron did I have? 35, right? Equals what is the molarity after I dilute it to a total of how many mils? The final solution is how many mils? 90. All right, so we got to find this new molarity. I got it to be 0.0972. And this is, again, the new concentration of my iron 3 nitrate. So now how do we find just the concentration of our iron 3 nitrate? This is moles of FeNO3 per liter. What do I want for every 1 mole of FeNO3? I want just nitrate ions. How many? 3 moles of just the nitrate. Does that make sense, all of this, from beginning to end? It's important. Again, this is how we take what you learn in Chem 1 and twist it up a notch, make things a little more thought-provoking. So I got 0.292. Where these problems get to be crazy is if they choose something that forms a precipitate but has one of the ions of that in excess. So you have to figure out how much forms a precipitate, which then you have to subtract from the original amount of moles, and then whatever moles is left over. So they can get pretty scary hairy. So just be aware of that. All right? Yes? We mixed, in our previous problem, we mixed, the question was, for people at home, where did the 90 mils come from? If you look up at number 10, we mixed 35 mils with 55 mils. Whenever we do a dilution, we look at the total volume. We diluted to 90 mils total. Do you see that? 35 plus 55 is 90. Okay? All right. That's it for the day. I'm going to give you some time. You only have like 9 minutes, but you can knock out a few homework problems. Do you get it? Okay.